December 7th, 1942, Newport News, Virginia. 1 year to the day after Pearl Harbor burned. The night shift at Newport News Shipbuilding had just begun, and the air tasted of metal and salt. Under the harsh glare of floodlights, a welder named Raymond Chen crouched inside the skeletal hull of what would become USS Franklin, keel number CV-13. His torch hissed blue-white against the steel, casting dancing shadows across the ribbed interior of the carrier's frame. He was running his bead at an angle the Navy inspectors had never authorized, not perpendicular to the joint, as the manual specified, but tilted 15 degrees forward, moving faster, hotter, deeper. It wasn't reckless, it was calculated, and if anyone noticed, it could get him fired, blacklisted, maybe worse. But Raymond had done the math in his head 100 times. The old way, the approved way, was too slow, and America didn't have time to be slow anymore. The war in the Pacific was a bleeding wound. 6 months after Pearl Harbor, the United States Navy had lost Lexington at Coral Sea, Yorktown at Midway, Wasp near Guadalcanal, and Hornet at Santa Cruz. 4 fleet carriers, gone. Only Enterprise and Saratoga remained operational in the entire Pacific theater. Meanwhile, the Japanese still had 6 carriers prowling the ocean, and the invasion of the Philippines was only months away. Admiral Ernest King, Chief of Naval Operations, had sent a classified memo to every major shipyard on the East Coast. The message was 3 words long: build them faster. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Essex class program had been conceived before the war, back in 1939, when the Washington Naval Treaty still limited carrier tonnage and America still believed diplomacy might prevent catastrophe. The first 3 hulls, Essex, Lexington, and Bunker Hill, had their keels laid in 1941 before anyone imagined how desperately they'd be needed. The original timeline projected 36 months from keel to commission, 3 full years per ship. That pace would lose the war. By December of 1942, with Franklin's keel barely 2 weeks old, the Navy had already slashed that timeline in half. 18 months, they said, maybe 20 if the weather turned. The shipyards laughed, then looked at the production schedules, then stopped laughing. 18 months meant every single step of construction had to be reimagined. Every weld, every rivet, every plate of steel had to be faster without being weaker. And the men on the floor, the ones actually building these ships, knew something the engineers in Washington didn't. Speed wasn't just about working harder. It was about working differently. Raymond Chen had been welding since he was 16, learning the trade in his father's shipfitter shop in San Francisco before the yard. Hired him in 1941. He wasn't an engineer. He didn't have a degree. But he understood metal the way a pianist understands keys, instinctively, through 10,000 hours of repetition and failure. And he'd noticed something about the way the Navy wanted these carriers built. The approved technique, straight perpendicular welds with slow, even passes, created beautiful seams, perfect textbook joins that any inspector would approve. But they also created something else: stress. When you welded perpendicular to a joint, the heat concentrated in a narrow zone. The metal expanded rapidly, then contracted as it cooled, pulling inward with enormous force. In a small structure, that stress dispersed harmlessly. But in a ship the size of an Essex-class carrier, 872 feet long and weighing 27,000 tons, those tiny zones of stress multiplied across thousands of welds. They became pressure points, invisible fractures waiting to happen when the hull flexed under heavy seas or took a hit from a bomb. Raymond had seen it before on the smaller destroyers, cracks appearing along seams that had passed every inspection, plates warping overnight as residual tension finally released. The old riveted ships didn't have this problem. But the Essex class was fully welded, bow to stern, one continuous steel skin. That continuity made it strong, but it also made it vulnerable, unless you changed how you laid the bead. He'd started experimenting 3 months earlier, on scrap plates during his lunch breaks, angling the torch forward, increasing the travel speed, letting the arc stretch slightly ahead of the puddle. The welds looked different, rougher, less symmetrical. The angled pass distributed heat across a wider area, reducing the sharp temperature gradients that caused warping. The metal breathed instead of gasping. He'd tried to explain it to his foreman, a man named Dutch Kellerman, who'd been building ships since before Raymond was born. Dutch had listened politely, examined the test plates, then shaken his head. Navy specs say perpendicular. Chen. We follow Navy specs. You want to redesign their welding manual? Go get yourself an engineering degree. But Raymond couldn't let it go. Every night, as he worked his way through Franklin's hull, he watched the other welders following procedure. He watched the plates bow slightly as they cooled. He watched the fitters come through afterward with hydraulic jacks, forcing the warped steel back into alignment, adding more stress, more tension. And he watched the calendar. December 1942. Franklin was scheduled to launch in October of 1943, 10 months away. The Navy needed her in the Pacific by January of 1944, barely 14 months from now. At the current pace, they'd never make it. So Raymond made a decision. He stopped asking permission. On the sections where inspectors rarely checked, the interior frames, the double-bottom compartments, the spaces hidden behind equipment, he used his angled technique, faster, hotter, smoother. He finished his assignments 30 minutes ahead of schedule every shift, which meant he could help other welders finish theirs. Within 2 weeks, his entire section was ahead of schedule. Within a month, Dutch Kellerman noticed. Chen, what the hell are you doing different? Dutch had cornered him one night near the fabrication shed. Arms crossed, expression unreadable. Raymond hesitated. This was the moment he got fired. I'm angling the torch, Dutch, 15 degrees forward. It distributes the heat better, reduces warping. The welds are just as strong, I've tested them. Dutch stared at him for a long moment. Then he said, Show me. After sample while Dutch watched. When they were done, Dutch picked up one of the plates, turned it over in his hands, ran his finger along the bead. This ain't in the manual. No, sir. Navy inspectors see this. They'll reject the whole section. Yes, sir. Dutch was quiet for another moment. Then he said, How much faster? 20%. Maybe 30 if the whole crew learns it. Dutch looked at the calendar on the shed wall, looked at the production schedule, looked back at Raymond. Teach the night shift. Don't tell the inspectors. If this goes sideways, it's on you. Understood. That night, Raymond Chen became an unofficial instructor. He gathered the welders in his section, 12 men and 3 women, and showed them the technique. Some picked it up immediately. Others struggled, their hands too trained in the old method to adjust. But within a week, the entire night shift on Franklin's hull was using the angled pass. Within 2 weeks, the warping problems that had plagued earlier sections disappeared. The plates stayed true. The fitters stopped needing their jacks, and the production timeline, for the first time since Pearl Harbor, started moving in the right direction. But speed alone wouldn't save the program. The Essex-class carriers were the most complex warships ever attempted by the United States Navy. They displaced nearly 30,000 tons fully loaded, carried 90 aircraft, and required 4,000 men to operate. Every carrier needed 250,000 individual parts, from massive turbine blades to tiny electrical fittings. The supply chain stretched from Pennsylvania steel mills to California wire manufacturers, all feeding into 5 shipyards scattered across the East Coast. Newport News had been designated the lead yard, responsible for 7 carriers. Bethlehem's Fall River Yard in Quincy, Massachusetts, would build 4. The Navy yards at Brooklyn, Norfolk, and Philadelphia would split the rest. At the peak of production, all 5 yards would be building Essex-class carriers simultaneously, a feat of industrial coordination that had never been attempted before. And every single one of them faced the same problem Raymond Chen had identified. The approved methods were too slow. The breakthrough hadn't come from the top down. It had come from the floor up, from the welders and fitters and electricians who actually touched the steel. And the innovation wasn't just in welding technique. It was in design philosophy. The Essex class, unlike every carrier before it, had been designed with one principle in mind: flat surfaces. Wherever possible, the hull used straight, flat plates instead of complex curves. The flight deck was a simple rectangle. The hull sides were vertical, not tapered. The internal bulkheads ran in straight lines. To a naval architect, this looked crude, inelegant. Traditional warships had graceful curves, compound angles, hulls shaped like living things. The Essex looked like a floating shoebox. But those flat surfaces meant something revolutionary. They could be prefabricated. Instead of shaping each plate individually on the ship, welders could assemble entire sections in fabrication sheds, giant modules weighing hundreds of tons, then lift them into place with cranes. It was mass production applied to warship construction, an idea borrowed from Henry Ford's automobile factories. The man who'd pushed hardest for this approach was Commander Leslie Knisken, the Bureau of Ships officer who'd led the Essex design team. Knisken had never built a ship before the war. He was a systems thinker, trained in industrial engineering, and he'd looked at traditional shipbuilding the way an efficiency expert looks at a factory floor. Too many custom parts, too much hand-fitting, too much time wasted on unnecessary complexity. His design specifications for the Essex class had been radical. Use special treatment steel wherever possible, a nickel-chromium alloy that was, both structural and armor grade, eliminating the need for separate armor plating. Standardize every component, every pipe diameter, every electrical junction box. Make the ships as modular as possible, so damaged sections could be cut out and replaced at sea. And above all, make them simple to build. The Navy's old guard had hated it. They called the Essex class utilitarian, which was a polite way of saying ugly. They complained about the lack of armor on the flight deck, the exposed elevators, the squared-off bow that looked like it belonged on a cargo ship. But Knisken had one argument that silenced every critic. We can build 6 Essex carriers in the time it takes to build 2 of the old design. Which fleet wins the war? By December of 1942, his gamble was paying off. The first Essex-class carrier, USS Essex herself, had been launched in July and was nearly complete. The Spring, Yorktown, Intrepid, Hornet, Franklin, all on schedule for 1943. The assembly line carrier was becoming reality. But there was still a problem. Even with prefabrication, even with simplified designs, even with Raymond Chen's welding innovations, the carriers were complex machines. 4 boiler rooms, each with 2 Babcock and Wilcox boilers burning at 850 degrees Fahrenheit. 2 engine rooms with Westinghouse steam turbines, generating 150,000 shaft horsepower, electrical systems, hydraulic systems, aviation fuel systems, all packed into a hull that had to survive torpedoes, bombs, and kamikaze strikes. The margin for error was razor-thin. A single mistake in the welding could create a weak point that would fail catastrophically under stress. A single miscalculation in the armor placement could leave a vital space exposed. And the men building these ships, most of them, had never built a warship before. They were farm boys. From Iowa, factory workers from Detroit, immigrants from every corner of the world, trained in weeks to do jobs that used to require years of apprenticeship. Raymond Chen understood this better than most. Every night, as he moved through Franklin's hull, he saw the evidence of inexperience, welds that wandered off their seams, plates installed backward, electrical conduits routed through structural members. The inspectors caught most of it, but not all, and what they missed would only reveal itself later, at sea, under combat conditions. That terrified him more than any Japanese bomb. One night in January of 1943, as Raymond was finishing a seam in Franklin's engine room, he heard voices echoing through the hull, angry voices. He shut off his torch and listened. 2 men arguing, one of them Dutch Kellerman. Raymond climbed down from his scaffold and followed the sound to the aft bulkhead, where Dutch was standing with a Navy inspector, a thin man in glasses named Patterson. "I don't care how fast your boys are welding," Patterson was saying. "This section fails inspection. Look at this bead. It's at the wrong angle, not perpendicular to the joint. This is not Navy specification. Dutch's face was red. That weld is solid, Patterson. Stronger than the ones that meet your specs. I don't certify welds based on your opinion, Kellerman. I certify them based on the manual, and the manual says perpendicular. This entire section needs to be cut out and redone. Raymond's stomach dropped. That section represented 2 weeks of work. If it had to be redone, Franklin would miss her launch date, and if Franklin missed her date, the entire program would slip. He stepped forward before he could stop himself. Inspector Patterson, I'm the welder who laid that bead. Patterson turned, eyebrows raised. You're Chen? Kellerman says you're the one teaching this technique to the crew. Do you understand that you're in violation of Navy welding specifications? Yes, sir, but the specifications are wrong. The words hung in the air like smoke. Dutch closed his eyes. Patterson stared at Raymond with an expression somewhere between disbelief and fury. The specifications, Patterson said slowly, were written by the Bureau of Ships, by naval architects with decades of experience. And you, a welder with, 2 years of experience, think you know better? Raymond met his eyes. I think the specifications were written for riveted ships, sir. The Essex class is fully welded. The thermal dynamics are different. The stress distribution is different. The old technique creates pressure points that will fail under combat loading. My technique distributes that stress more evenly. Do you have engineering calculations to back that up? No, sir. I have test results. Test results you conducted yourself, with no oversight, using scrap metal. Yes, sir. Patterson shook his head. I'm rejecting this section, and I'm filing a report with the Bureau of Ships recommending that your welding certification be revoked. Raymond nodded slowly. But before you do that, I'd like to show you something. He led them to the fabrication shed, where he'd been collecting sample welds for 3 months. Dozens of plates, half welded with the approved perpendicular technique, half with his angled method. He'd labelled each one with the date, the temperature, the cooling time, and he'd subjected them to stress tests, bending them, heating them, freezing them, measuring the deformation. This is the approved method, Raymond said, holding up a plate that had visibly warped. You can see the distortion along the weld line. This is my method. He held up another plate, nearly flat. Same steel, same heat input, different result. Patterson examined the plates in silence. Then he said, This isn't a controlled experiment. The conditions aren't standardized. No, sir. But it's 3 months of data from actual production conditions. That's more than the Navy specs are based on. Patterson looked at Dutch, then back at Raymond. If I allow this technique, and one of these ships breaks apart at sea because of it, the blood is on your hands. If we stick to the approved technique, sir, and these ships arrive too late to stop the Japanese, the blood is on all of ours. For a long moment no one spoke. Then Patterson said, I want metallurgical analysis. I want stress calculations from an actual engineer, and I want it on my desk in 2 weeks. Until then, this section stays as is, but you don't teach this technique to anyone else. Understood? Yes, sir. 2 weeks later, Raymond Chen found himself standing in a conference room at the Bureau of Ships headquarters in Washington, surrounded by men in Navy uniforms and civilian suits. On the table in front of them were his sample plates, his test data, and a 20-page engineering analysis prepared by a metallurgist from MIT who'd been contracted to evaluate his technique. The metallurgist, a stern woman named Dr. Ellen Hartley, stood at the front of the room with a pointer. The data is conclusive, she said. Chen's angled welding technique reduces residual stress by approximately 35% compared to the perpendicular method. It also increases production speed by 20 to 30%, depending on the welder's skill level. More importantly, it reduces the incidence of cold cracking in thick section welds, which is critical for the Essex-class hull construction. A Navy captain raised his hand. Are you recommending we change the official welding specifications? I'm recommending we conduct full-scale trials, Doctor, Hartley said. If those trials confirm these results, then yes, the specifications should be updated. And if we don't update them? Then you'll continue building carriers that warp during construction, require excessive rework, and potentially develop stress fractures in service. The captain looked at Raymond. Where did you learn this technique? I didn't learn it, sir. I invented it. Out of necessity. And you're just a welder? Raymond felt the weight of the question. Just a welder, as if his hands, his experience, his 10,000 hours with a torch meant nothing compared to a diploma on a wall. But before he could answer, Dr. Hartley spoke up. With respect, Captain, some of the most important innovations in materials engineering have come from the shop floor, not the laboratory. Mr. Chen identified a problem, hypothesized a solution, and tested it empirically. That's the scientific method, regardless of where it happens. The captain nodded slowly. Trials, then. If they work, we'll update the specs. If they don't, we court-martial everyone in this room. He wasn't smiling. The trials took 4 weeks, 3 sample hull sections, built side by side at the Philadelphia Navy Yard, one using the approved, perpendicular technique, one using Raymond's angled method, and one using a hybrid approach. Each section was subjected to the same stress tests: hydraulic loading, thermal cycling, impact testing. Engineers measured every dimension before and after, looking for distortion, cracking, or deformation. The results weren't close. The perpendicular sections showed significant warping and micro-cracking under thermal stress. The hybrid sections performed better, but still showed distortion. Raymond's sections stayed true, with minimal warping and no detectable cracks. When the Navy's chief metallurgist presented the findings to Admiral King, the Chief of Naval Operations, King's response was reportedly 3 words: change the specs. On March 15, 1943, the Bureau of Ships issued Technical Bulletin 43-7, officially authorizing the angled welding technique for Essex-class carrier construction. The bulletin didn't mention Raymond Chen by name. It referred to the method as forward angle arc welding for reduced thermal distortion in thick-section plate joints. But every welder on every shipyard floor knew where it had come from. Within weeks, the new technique was being taught at all 5 carrier yards. Production speeds increased immediately. Warping problems, which had been causing delays on every ship, virtually disappeared. The rework rate dropped by 40%, and the timeline for completing Essex-class carriers shrank from 18 months to 15, then to 14. USS Franklin, keel number CV 13, the ship where it all began, was launched on October 14, 1943, just 10 months after her keel was laid. She was commissioned on January 31, 1944, barely 14 months from start to finish. The fastest major warship construction time in naval history. But Franklin was just one ship. By the time she slid into the water, 12 more Essex-class carriers were already under construction. Essex, herself, was already at sea. Lexington and Yorktown were in their final fitting out. Intrepid, Hornet, Wasp, Hancock, Bunker Hill, all rising from their building ways like steel mountains. And every single one of them was being built faster than anyone had thought possible, not because of some grand innovation from the top, but because a welder in Virginia had tilted his torch 15 degrees and refused to accept that the old way was the only way. Raymond Chen never became famous. His name never appeared in the history books, never earned a medal, never gave a speech to Congress. He stayed on the floor at Newport News, welding carriers until the war ended. After Franklin, he worked on Ticonderoga, then Randolph, then Shangri-La. He trained hundreds of welders, refined his technique, helped develop new methods for other parts of the ship. But he never stopped thinking about that moment in December of 1942, when he'd crouched inside Franklin's hull and decided to break the rules, because he understood something that took the Navy years to learn. Innovation doesn't always come from the engineers who design the ships. Sometimes it comes from the hands that build them. The Essex-class carriers would become the backbone of the Pacific Fleet, the ships that turned the tide at Leyte Gulf, Iwo Jima, and Okinawa. 24 would be completed by the end of the war, more fleet carriers than any nation had ever built. Not one would be sunk by enemy action, though several, including Franklin, would come terrifyingly close. And buried in their hulls, in thousands of welds running through their frames, was the legacy of a technique that shouldn't have worked, taught by a man who shouldn't have known better. The steel remembered, even if history didn't. By the spring of 1943, the impossible was becoming routine. Across 5 shipyards stretching from Massachusetts to Virginia, the United States was building aircraft carriers at a pace that defied every historical precedent. Where battleships once took 4 years to construct, Essex-class carriers were sliding into the water in 14 months. Where traditional wisdom said warships required meticulous hand-fitting and years of skilled labor, these new carriers were being assembled like automobiles, built from prefabricated modules and standardized parts. But speed had revealed a new problem, one that nobody at the Bureau of Ships had anticipated. The carriers were being built so fast that the Navy couldn't crew them. Lieutenant Commander Patricia Morrison discovered this crisis firsthand in April of 1943, when she arrived at the Brooklyn Navy Yard to inspect personnel readiness for USS Bonhomme Richard, then under construction on Shipway 4. Morrison was one of the few women in the Navy's Bureau of Personnel, a specialist in crew training and allocation. She'd been sent to Brooklyn to solve what her superiors called the Manning problem. The numbers told a grim story. USS Essex had commissioned in December with a crew shortage of 300 men. Lexington, commissioned in February, was missing 400. These weren't trivial gaps. They were gunners, radar operators, damage control specialists, the technical ratings that kept a carrier functioning in combat. And with 12 more carriers scheduled to commission in the next 18 months, the shortage was about to become catastrophic. "We're building ships faster than we can train sailors to man them," Morrison wrote in her initial report. "The bottleneck is no longer steel, it's people." The problem had roots in a decision made years earlier, before anyone imagined the scale of the war to come. Naval training programs, designed for peacetime expansion, required 6 months to a year to produce qualified personnel. Radar technicians trained for 9 months. Aviation mechanics for 8. Fire controlmen for 10. These lengthy programs made sense when the Navy commissioned 2 or 3 ships per year. But in 1943, with carriers launching every 6 weeks, the mathematics didn't work. Morrison spent 2 weeks at Brooklyn interviewing shipyard supervisors, observing construction, and analyzing the crew requirements for each Essex-class carrier. What she found surprised her. The ships weren't just being built faster, they were being built smarter. The standardized design meant that every Essex-class carrier was essentially identical. Same layout, same equipment, same systems. A radar operator trained on Essex could transfer to Yorktown without relearning anything. A damage control team drilled on Lexington could serve on any carrier in the fleet. Instead of training sailors in isolation at shore schools, then assigning them to ships, why not train them on actual carriers? Use the first ships of the class as floating academies, teaching crews on the same equipment they'd use in combat. Then transfer those trained crews to newly commissioned carriers, leaving behind a cadre of instructors to train the next batch. It was a radical idea. The Navy had never operated training programs aboard frontline warships, but Morrison wasn't proposing traditional training. She was proposing what would later be called on-the-job training at scale, using the ships themselves as classrooms and the early crews as a self-replicating pool of instructors. She presented the concept to Captain Harold Stassen, the Chief of Personnel Training at Bupers, in May of 1943. Stassen, a former Minnesota governor who joined the Navy after Pearl Harbor, understood political reality better than most officers. He saw immediately what Morrison was proposing. Conscript the ships into the training program. "You want to turn my carriers into high schools," Stassen said. "I want to turn them into factories, sir. Factories that produce trained sailors instead of steel. And if the Japanese attack while we've got half-trained crews aboard, then we'll have half-trained crews who know their ships intimately, rather than no crews at all. Stassen authorized a trial program on USS Yorktown in June. The ship, commissioned in April, had sailed to Pearl Harbor with a green crew, most of them fresh from boot camp. Morrison flew out to Hawaii with a team of training specialists and spent 3 weeks aboard, observing operations and developing curriculum. What she found was chaos, but productive chaos. The crew was learning by necessity, every watch section figuring out their systems through trial and error. Radar operators memorized their scopes by tracking real aircraft. Gunners calibrated their weapons by firing live ammunition at towed targets. Damage control teams drilled with actual fires, actual flooding, actual emergencies. It was brutal, exhausting, and remarkably effective. Morrison designed a program that would formalize this chaos. Each Essex-class carrier, upon commissioning, would receive a nucleus crew of experienced personnel from earlier ships, about 20% of the total complement. These veterans would form the backbone of each division, training the remaining 80% during the shakedown cruise. After 6 months, half of that trained crew would transfer to the next carrier, taking their knowledge with them and starting the cycle again. It was a pyramid scheme for personnel, each generation of sailors training the next. And it worked because the ships were identical. A sailor trained on Yorktown could step aboard Intrepid and find everything in the same place, wired the same way, operated with the same procedures. The Essex class wasn't just a fleet of carriers. It was a fleet of carbon copies. The program launched officially in August of 1943, with USS Essex herself serving as the model. Her crew, by then veterans of raids on Marcus Island and Wake, provided cadres for Yorktown, Intrepid, and Hornet. Those crews, in turn, would seed Wasp, Franklin, and Hancock. By the end of the year, every Essex-class carrier commissioned would carry knowledge inherited from the first ship. A living transmission of expertise passed from crew to crew like a relay race across the Pacific. But personnel was only one piece of the puzzle. As production accelerated through the summer of 1943, a different crisis emerged, this one involving the very material the ships were built from: steel. The United States was producing more steel than any nation in history, but the Essex program consumed it faster than the mills could deliver. Each carrier required 15,000 tons of steel plate, plus another 5,000 tons for equipment, pipes, and machinery. With 24 carriers under construction simultaneously, that meant 380,000 tons of steel, committed to the program alone, enough to build 6 battleships or 40 destroyers. And not just any steel. The Essex design specified special treatment steel, a nickel-chromium alloy that was both stronger and lighter than conventional armor plate. STS could serve as structure and protection simultaneously, eliminating the need for separate armor layers. But it was also expensive, difficult to produce, and in desperately short supply. By June of 1943, the steel mills were 6 months behind on STS deliveries. The yards had enough conventional plate to keep building, but without STS for the critical areas, the hangar decks, the machinery spaces, the magazines, the carriers would be vulnerable. The Bureau of Ships faced an impossible choice: delay construction until the mills caught up, or build with inferior materials and accept the risk. Then someone at Bethlehem Steel, a metallurgist named Gordon Cross, suggested an alternative. What if they didn't need as much STS as the specifications called for? What if the design was overbuilt, using armor-grade steel in places where regular structural steel would suffice? Cross had been analyzing the Essex blueprints and noticed something curious. The specifications called for STS in virtually every structural member below the hangar deck, thousands of tons per ship. But most of those members would never see direct enemy fire. They were interior bulkheads, frames, deck beams, protected by layers of outer hull. Using STS, there was like wearing a bulletproof vest under your shirt, under your jacket, under your coat. Redundant. He proposed a modified design that used STS only in the critical zone: the outer hull, the hangar deck, the fourth deck, and the magazines. Everything else would be high-tensile structural steel, still strong, still reliable, but much faster to produce. The modification would reduce STS requirements by 40% per ship, freeing up enough material to keep the program on schedule. The Bureau of Ships was skeptical. The original design had been calculated meticulously, every plate justified by survivability studies and damage control analyses. Reducing armor protection, even in supposedly safe areas, felt like gambling with sailors' lives. But the alternative was worse. Carriers arriving late, missing the battles they were desperately needed for. In July, the Navy authorized trials on 2 carriers, then under construction, USS Princeton at the Philadelphia Navy Yard and USS Belleau Wood at the New York Shipbuilding Yard in Camden. Both were Independence-class light carriers, smaller cousins of the Essex, built on converted cruiser hulls. They'd serve as test cases. If the modified design held up under combat conditions, it would be applied to the Essex class. Princeton and Belleau Wood commissioned in late February and March of 1943 and deployed to the Pacific by summer. They saw action at the Gilbert Islands in November, launching strikes against Tarawa and Macon. Flawlessly, their modified structures showing no weakness under combat stress. The Navy approved Cross's modification in December, and by January of 1944, every Essex-class carrier under construction was being built with the reduced STS specification. The savings were immediate. Steel deliveries caught up, construction schedules stabilized, and the modifications introduced an unexpected benefit. The carriers were lighter. Replacing heavy STS with conventional steel reduced displacement by nearly 800 tons, which translated into higher speed and better fuel efficiency. The Essex class had been designed for 33 knots. The modified ships could touch 34. But not everything could be solved with clever engineering. Some problems required brute force and relentless determination, and in the winter of 1943, as the carriers began reaching the fleet in numbers, they revealed a flaw that no amount of redesign could fix. They were too complex for green crews to operate effectively. Commander William Halsey, Jr., son of Admiral Bull Halsey and executive officer of USS Intrepid, identified the issue in a brutally honest report filed in December of 1943. Intrepid had just completed her shakedown cruise and was preparing for deployment to the Pacific. Her crew, nominally trained, had struggled with basic operations. Aircraft launches took twice as long as doctrine required. Damage control drills descended into confusion. Navigation errors were common, and in one terrifying incident, a fuel line rupture in the hangar deck had nearly caused a catastrophic fire. "This crew is not ready for combat," Halsey wrote, "and no amount of training will make them ready in time. The Essex class is too large, too complicated, too demanding for sailors with 6 months of experience. We're asking farm boys from Iowa to operate machinery more complex than a Ford factory, and then expecting them to do it under fire." His solution was radical: simplify the operations. Not the ship, but the procedures. Instead of the Navy's traditional approach, complex protocols that assumed experienced crews, develop simplified checklists that even novices could follow. Break every operation down into discrete steps, numbered, verified, impossible to skip. Treat the crew like assembly line workers, each person responsible for a small, specific task, repeated until it became instinct. It was industrial efficiency applied to naval operations, the same philosophy that had revolutionized the shipyards, now brought aboard the ships themselves. And it worked. Halsey's team spent 2 months developing what they called the Intrepid Standard Operating Procedures, a thick manual of checklists covering every operation from starting the boilers to recovering aircraft. Each procedure was tested, refined, and tested again until even the greenest sailor could execute it correctly. When Intrepid deployed to the Pacific in January of Tulav, 1944, her crew performed with a precision that astonished the task force commanders. Aircraft launches that had taken 40 minutes now took 15. Damage control teams responded to simulated casualties in half the time, and when Intrepid took a torpedo hit off Kwajalein in February, the crew contained the flooding, maintained power, and kept her operational, a feat that would have been impossible with traditional training. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Intrepid procedures were immediately distributed to every Essex-class carrier in the fleet. By March, they'd become the standard for all Pacific carrier operations. And the philosophy behind them: reduce complexity, standardize procedures, train for specific tasks rather than general competence, would reshape naval training for the next 50 years. But the most profound change wasn't in the ships or the procedures. It was in the industrial ecosystem that supported them. By early 1944, the Essex program had evolved into something unprecedented. A fully integrated production system stretching from ore mines to battle groups, coordinating steel mills, shipyards, equipment manufacturers, training facilities, and fleet operations into a single, synchronized machine. At the center of this machine was the Bureau of Ships, specifically the Essex Coordination Office, a small department established in October of 1943 to manage the overwhelming complexity of building 24 identical carriers simultaneously. The office was led by Rear Admiral Edward Cochrane, a naval architect who'd helped design the Essex class and understood both the technical and logistical challenges. Cochrane's team developed what they called the Master Production Schedule, a living document that tracked every component of every carrier, from keel laying to commissioning. Schedule identified bottlenecks before they occurred, redirected materials from ships ahead of schedule to those falling behind, and coordinated the 5 shipyards so they weren't competing for the same scarce resources. It was supply chain management at a scale never attempted before, and it required constant adjustment. When Newport News ran short of turbine blades in November, the schedule shifted deliveries from the Brooklyn yard, which was ahead on its ship. When the Philadelphia yard lost a crane to storm damage in December, the schedule rerouted prefabricated sections through Norfolk. The system was fluid, responsive, almost organic. But it only worked because the ships were identical. That standardization, which had seemed like a compromise when the Essex was designed, had become the program's greatest strength. Parts were interchangeable. Workers trained at one yard could transfer to another without retraining. Lessons learned on one ship applied instantly to all the others. The Essex class wasn't 24 separate projects. It was one project, built in 24 locations. By March of 1944, the production system had reached peak efficiency. USS Franklin was at sea, conducting strikes on the Marianas. USS Hancock was in her final trials. USS Ticonderoga was fitting out at Norfolk. USS Randolph was being assembled at Newport News. And USS Shangri-La had just had her keel laid at the same yard, occupying the slip Franklin had vacated 14 months earlier. The cycle time from keel to commission had stabilized at 15 months, faster than anyone had predicted, and the quality had improved. Early ships like Essex and Lexington had required extensive post-commissioning modifications. Later ships like Hancock and Ticonderoga incorporated those changes during construction, arriving at the fleet fully combat-ready. The Essex class had become a machine that built itself better with each iteration, and at the heart of that machine still, largely invisible to history, were the thousands of workers who'd transformed warship construction from a craft into an industry. People like Raymond Chen, still welding at Newport News, now training his 3rd generation of welders. People like Patricia Morrison, coordinating crew assignments from a desk in Washington, ensuring every carrier had the personnel it needed when it needed them. People like Gordon Cross at Bethlehem Steel, calculating stress loads and metallurgical properties to squeeze another week out of the construction schedule. They were the assembly line that built the Armada, and their innovation wasn't in grand design or brilliant strategy. It was in the accumulated wisdom of 10,000 small improvements, each one shaving hours off the schedule, each one making the next ship slightly better than the last. By June of 1944, as Allied forces stormed the beaches of Normandy, 9 Essex-class carriers were operational in the Pacific. Essex, Yorktown, Intrepid, Hornet, Franklin, Wasp, Hancock, Bunker Hill, and Lexington formed the backbone of Task Force 58e, the most powerful naval formation ever assembled. Together, they carried more than 800 aircraft, more air power than the entire Imperial Japanese Navy possessed. And they were just the beginning. 7 more carriers were fitting out or in trials. 8 more were under construction. The Japanese, looking at intelligence reports, must have felt they were fighting a nation that could conjure warships from thin air. In a sense, they were, because the Essex-class program had done something unprecedented in naval history. It had industrialized war at sea. The carriers weren't craft-built masterpieces, each one unique and precious. They were products, manufactured to specification, delivered on schedule, and immediately replaced if lost. That shift in philosophy, from scarcity to abundance, from craftsmanship to production, would define American naval power for the next half-century. The supercarriers that would follow, the Midway class, the Forrestal class, the Nimitz class, all inherited the lessons learned building the Essex: standardization, modularity, rapid construction, industrial discipline applied to naval architecture. But in 1944, those lessons were still being learned, often through painful experience. And nowhere was that pain more evident than in what happened to USS Franklin, the ship where it all began, on a cold March morning off the coast of Japan. The story of that morning, and what Raymond Chen's welds endured when they were tested by fire, would prove whether innovation measured in degrees of torch angle could survive the ultimate test: combat. March 19th, 1945. 50 miles off the coast of Japan. The sky was the colour of old pewter, heavy with clouds that pressed down on the sea like a lid on a pot. USS Franklin, carrier number CV-13, steamed at 25 knots as part of Task Group 58. 2, closer to the Japanese homeland than any American carrier had ever ventured. It was just after dawn, and the flight deck was crowded with aircraft, 31 planes armed and fueled, preparing for the morning strike against Kobe Harbor. Below deck, in the forward damage control station, a young sailor named Tommy Pritchard was reviewing his checklist for what felt like the 100th time. Pritchard was 20 years old from a farm outside Omaha, and he'd been aboard Franklin for exactly 4 months. He'd never seen combat, never experienced anything more violent than a storm off the Philippines. But he'd memorized the intrepid procedures, every word, every step, because his chief had told him that in an emergency, thinking would get you killed. Following the checklist would save your life. At 7:15 a.m., Franklin turned into the wind and began launching aircraft. Hangar deck, crews were spotting the next wave, 22 aircraft loaded with 500-pound bombs and rockets, their fuel tanks topped off for the long flight to the target. At 7:08 a single Japanese bomber, a Yokosuka Dichteri I Judy, dropped out of the cloud layer directly above Franklin. The combat air patrol had missed it. The radar hadn't picked it up, and the ship's gunners had no time to react. The bomber released 2 550-pound semi-armor-piercing bombs from 3,000 feet, then vanished back into the clouds. The first bomb hit the flight deck centerline, just forward of the island, and punched through the wooden deck like it was paper. It penetrated to the hangar deck, detonated, and instantly killed everyone in the forward section. The explosion triggered a massive fire that spread through aircraft, fuel, and ammunition. The second bomb hit aft, tearing through 2 decks and igniting more fires in the crew spaces below. What happened next would become the most devastating attack on any US warship that survived the war. The initial explosions set off a chain reaction. Fuel from ruptured aircraft tanks spread across the hangar deck, creating rivers of fire. Rockets, the massive 11.75-inch Tiny Tim, rockets that each aircraft carried, ignited and screamed through the ship like horizontal meteors, punching holes through bulkheads, starting new fires, killing men who thought they were in safe spaces. Within 5 minutes, Franklin was transformed from a warship into an inferno. Smoke poured from her hull, black and thick, visible for 30 miles. Her steering failed, her radios died, her combat information center was obliterated, and deep in her engineering spaces, the temperature began to rise as fires ate through the ventilation systems, threatening to reach the fuel tanks and magazines. Captain Leslie Gairis, Franklin's commanding officer, stood on the bridge and faced a decision no captain ever wants to make. His ship was dead in the water, listing 13 degrees to starboard, and every indicator suggested she was doomed. The cruiser USS Santa Fe had pulled alongside, evacuating wounded. 832 men were already dead or missing, more casualties than any ship had suffered except USS Arizona at Pearl Harbor. Standard procedure said abandon ship, scuttle her before she became a floating bomb. But Garis looked at the hull beneath his feet, at the steel that Raymond Chen and thousands like him had welded together 30 months earlier, and he made a different decision. "We're not abandoning this ship," he told his executive officer. "Tell damage control to fight the fires. Tell engineering to get me power. We're bringing Franklin home." Tommy Pritchard heard the order through the Yedden MC speakers in his damage control station, and for a moment he thought the captain had lost his mind. The ship was dying. Everyone could feel it. The way the deck trembled with each explosion, the way the heat was building even in supposedly protected spaces. But then his chief, a grizzled boatswain's mate named Kowalski, slapped his shoulder and said, "You heard the man. Get your gear. We've got fires to fight." Pritchard followed Kowalski forward, toward the hangar deck, and entered hell. The space was filled with smoke so thick he couldn't see his own hands. The heat was overwhelming, like standing in front of a blast furnace. Somewhere in the darkness, ammunition was still cooking off, each explosion sending shrapnel whistling through the smoke. Men were screaming, some for help, others just screaming because the pain was too much to contain. Kowalski found a fire hose, turned it on, and pushed forward into the smoke. Pritchard followed, holding onto the chief's belt, because he'd lost all sense of direction. They advanced 5 feet, 10 feet, 15, the water from their hose turning instantly to steam. And then Pritchard's foot hit something soft. A body. He knelt down, felt for a pulse, found nothing. He moved forward and hit another body. Then another. The hangar deck had become a tomb. But Kowalski kept pushing forward because somewhere ahead, through the smoke and fire, was a bulkhead door that led to the aft section, where men were still alive and trapped. If they could reach that door, seal it, they could contain the fire to the forward spaces, and maybe, just maybe, save the aft 2/3 of the ship. They fought for 3 hours. Not just Kowalski and Pritchard, but 300 men scattered throughout Franklin's hull, each team following the same procedures, the same checklists, working blind, working by instinct and training. Host teams advanced through the smoke, repair parties sealed bulkheads, engineering crews rerouted power around damaged sections, and slowly, impossibly, they began to win. By 10 a.m., the major fires in the hangar deck were under control. By noon, engineering had restored partial power to the steering. By 3 p.m., Franklin was making way, limping at 3 knots, towed by the cruiser USS Pittsburgh, while damage control teams continued battling spot fires throughout the ship. And through it all, Raymond Chen's welds held. The explosions should have torn Franklin apart. The fire should have warped her frame, buckled her decks, caused catastrophic structural failure. But the welds, those thousands of angled passes laid down in the winter of 1942, distributed the stress instead of concentrating it. The hull flexed, groaned, absorbed punishment that would have broken a traditionally built ship, and it held. Lieutenant Commander Joseph O'Callaghan, Franklin's chaplain, would later receive the Medal of Honor for his actions that day. He'd organized firefighting parties, led men through burning spaces, administered last rites while standing in ankle-deep fuel. But in his official report, he wrote something that most historians overlooked. The ship's structure performed beyond all expectation. Despite catastrophic damage, the hull remained intact, bulkheads held, and frame members did not fail. Franklin survived because she was built to survive. The journey home took 12 days. Franklin limped across 5,000 miles of ocean, damaged but defiant, her crew living on deck because most interior spaces were uninhabitable. When she finally entered New York Harbor on April 28, 1945, more than 100,000 people lined the shore to watch. She was a wreck, blackened and broken, her flight deck torn open, her island scorched. But she was afloat, and she would never sail again. The damage was too extensive, the repairs too costly. On February 17, 1947, USS Franklin was decommissioned at Bayonne, New Jersey, and placed in reserve. She would never be modernized, never see Korea or Vietnam like her sisters. But in a strange way, that made her more valuable. She became a permanent testament to what the Essex program had achieved, a ship that survived the unsurvivable because thousands of workers had built her right. Raymond Chen read about Franklin's return in the newspaper while eating breakfast at a diner near Newport News. He was working on Shangri-La by then, the 22nd Essex-class carrier, and the story hit him hard. That was his ship. Those were his welds. He'd laid the first beads in her hull more than 2 years earlier, when the technique was still experimental, still controversial, still just a crazy idea from a welder who didn't know better than to break the rules. He never visited Franklin in person, never sought recognition, never told his story to reporters. But years later, in an interview conducted by a naval historian researching the Essex program, Raymond would say something that captured the essence of what had been accomplished. We didn't build 24 carriers. We built one carrier, 24 times. And every time we built it better. That's not innovation. That's just paying attention. By the war's end in August of 1945, 17 Essex-class carriers had seen combat. They'd launched more than 60,000 sorties, destroyed more than 5,000 enemy aircraft, and sunk or damaged hundreds of ships. Not one had been lost to enemy action, though several, like Franklin and Bunker Hill, had come terrifyingly close. And 7 more carriers were still under construction, ships that would never see World War II but would form the backbone of American naval power through Korea, Vietnam, and into the Cold War. The final Essex-class carrier, USS Oriskany, wasn't completed until 1950, 5 years after the war ended. By then, the design was obsolete, the product of a wartime emergency that no longer existed. But Oriskany incorporated every lesson learned from her 23 sisters, every modification, every improvement. She was the perfected version, the end result of 5 years of continuous refinement. And she would serve longer than any other carrier in her class, finally decommissioning in 1976 after 31 years of service. When she was scuttled as an artificial reef off Pensacola, Florida, in 2006, the Navy diver who placed the final charges reported that her hull was still solid, her welds still sound. After 6 decades of service and 30 years underwater, the steel remembered. The Essex program had cost approximately $1.4 billion, more than $20 billion in modern currency. It had employed more than 200,000 workers across 5 shipyards. It had consumed 15% of America's total steel production during the war years. And it had produced not just 24 carriers, but a revolution in how warships were designed, built, and operated. The standardization principles pioneered by the Essex program would be applied to every major warship class that followed. The training methods developed by Patricia Morrison would become the foundation of modern naval personnel systems. The welding techniques refined by Raymond Chen would be codified into specifications used worldwide. Even the production management systems created by Admiral Cochrane's Coordination Office would influence post-war industrial practices far beyond shipbuilding. But perhaps the program's most lasting legacy was philosophical. Before the Essex class, naval power was measured in individual ships, each one a precious asset that took years to build and couldn't be replaced. After the Essex class, naval power was measured in production capacity, the ability to build fleets instead of ships, to replace losses faster than enemies could inflict them. That shift, from scarcity to abundance, would define the American approach to military power for the next 75 years. It's why the United States builds supercarriers that cost $13 billion each and take 5 years to construct, while also maintaining the industrial base to build more if needed. It's why American military doctrine assumes that losses can be replaced, that time is on our side, that industrial capacity ultimately wins wars. The Essex class taught America that you don't win wars by building the perfect weapon. You win by building the good enough weapon in overwhelming numbers. then improving it faster than your enemy can counter it. That was the real innovation, not in the ships themselves, but in the system that produced them. Today, 4 Essex-class carriers survive as museum ships: USS Yorktown in Charleston, South Carolina, USS Intrepid in New York, USS Hornet in Alameda, California, and USS Lexington in Corpus Christi, Texas, the last to decommission, in 1991, almost 50 years after her launch. Visitors walk their decks, tour their hangar bays, stand on their flight decks and imagine what it was like when they ruled the Ford Pacific. But what they can't see, what no museum placard explains, is the invisible history built into those hulls. The welds laid by Raymond Chen and 10,000 welders like him, each one a tiny defiance of procedure, each one a small bet that there was a better way. The procedures written by Patricia Morrison, ensuring that green crews could operate complex machines under fire. The steel specified by Gordon Cross, lighter and stronger because someone questioned whether the original design was necessary. The Essex-class carriers weren't built by geniuses or visionaries. They were built by ordinary people who paid attention, who noticed problems, who had the courage to suggest solutions even when those solutions contradicted accepted wisdom. The innovation happened on the factory floor, in the training schools, in the damage control stations. It happened in 10,000 small moments when someone said, "What if we tried it this way instead?" That's the story no one tells about. World War II. Not the battles won by brilliant generals, but the wars won by competent workers who cared enough to do their jobs a little bit better each day. The Essex program was their victory, built one weld at a time, one procedure at a time, one lesson learned at a time. And the lesson itself, the one that echoes across 8 decades, is simple. Innovation doesn't require permission. It requires courage. The courage to challenge specifications, written by people who've never touched a torch. The courage to simplify procedures designed by people who've never operated under fire. The courage to question whether the way things have always been done is actually the way things should be done. Raymond Chen had that courage in December of 1942 when he tilted his torch 15 degrees and decided that the Navy's specifications were wrong. Patricia Morrison had it when she proposed using frontline carriers as training platforms. Gordon Cross had it when he calculated that the Essex class was overbuilt and could be made lighter without being weaker, and 300 men aboard USS Franklin had it on March 19, 1945, when they refused to abandon their ship despite every rational reason to do so. They weren't heroes in the traditional sense. They didn't storm beaches or fly into enemy fire, but they changed the war just as surely as the soldiers and pilots did, because they changed how America fought. They turned warship production from a craft into an industry, from an art into a science, from something done slowly and carefully into something done fast and right. The Essex-class carriers were their monument. 24 steel islands that carried American power across the Pacific, each one identical, each one slightly better than the last, each one proof that sometimes the best way to win a war is to build the tools of victory faster than the enemy can destroy them. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.